2G is inverse functions, and I know you guys already know a little bit about what an inverse is. You've used inverse operations all the time. Carrie used inverse operations when she solved that problem. It happens a lot. But we're going to talk about today's inverse functions. Don't forget your stat box. We're going to come to the stat box. I don't want to say the middle today, but in between two different ideas, we're going to come to the stat box and then finish it out. And just like a lot of this stuff, we're first going to talk about algebraically, how can we do this, and then we're going to talk about graphically, how can we do this. So we'll have both parts there. Oops. So an inverse function undoes the original function, just like the adding undid the subtracting, and subtracting undoes adding, and all that stuff that we've been working on and you've been doing since you were in Algebra 1, however long ago that was. That's what that inverse function is. And the symbol for inverse function is this -1 that's sort of in almost like an exponent spot, I guess. So if you've got f, and then you see the f we know means the function, this little -1, it means inverse. So we want to make sure that we use proper notation as we go about this today. Have you guys ever seen this little -1 anywhere on any functions before? Does anyone remember where they saw it? That's the question. Remember this? Yeah. So what this meant is that this was the inverse of tangent. It would undo whatever the tangent function did. Now, we're not getting into trig right now, but I just wanted to bring your attention to, you have seen that little -1 notation before. It's on your calculators you look at all the time. So kind of just keep that in mind. So we are going to do 2 examples finding the inverse algebraically, except for I'm going to get ahead of myself. First, we're going to talk about how we find it algebraically. It's called variable interchange. So to find the inverse algebraically, you switch the x and the y variables, and then you solve for y. So I'm going to really kind of take it slow at first when I go through this, just to kind of show you my style so I don't skip any steps and I'm not rushing. And then I'm sure you'll find your own pace and what works for you. But what we do is we put y in the x spots, all the x spots. If there's more than one, we'll put x in all the y spots. And then we will solve for y. We'll have to get y by itself. So there are different levels of difficulty just based on how complex a function is or isn't. And this will come back up as well. Like, it's not just like a chapter 2 thing. Like, we'll take a look at it in, I don't know if we'll be ready to in chapter 3, but in chapter 4 we'll take a look at it. So remember this process of variable interchange. So now I can talk about the examples. We're going to do 2 examples of solving it algebraically. We're going to do 2 show that examples that are also algebraically. We'll hit that stat box, and then we'll talk about how we can also do this graphically. So f of x is 2x plus 7. And we're gonna come back to f of x in one of our show that problems. So make sure your work is nice and clear so you can see what you do, because we are going to come back to it. Now, what we just talked about was with variable interchange. You put x where the y is, and we put y where the x is. Is y in my function right now? Yes and no, right? So this might seem like a silly step, and you might skip this step depending on how you feel, but I usually rewrite it so I can see where the y is. We know f of x equals y, and I think that's why we had the answer of yes and no, it's there, but not quite there. I take that step. Now that I take that step, I can perform my variable interchange, and I just switch these. So I write x equals 2y plus 7. So where the x is, I put y, where the y is, I put x. Now from here on out, I know you guys have the skills to do this. You just use your inverse operations to isolate y. So the opposite of plus 7 is minus 7. So I know I would write this as x minus 7 because we can't really subtract that. Equals 2y. I've got to get y by myself. What's that last step? What was that? Yeah, divide by 2. So those will cancel out. So I end up with x minus 7 over 2 equals y. We are going to finish it off with the proper notation, but are there any questions about that process of getting y by itself or changing those variables? So then my answer would be, instead of y, I'm going to use that inverse notation. So the inverse of f is, where are we here? X minus 7 divided by 2. Especially when I look at your work, I want to be able to see that you change those I don't know why I keep saying like inner something, but change those variables so I can see that you've got that concept down, and then the rest of your work there. All right, so g of x is what we're going to do next. So another function, and I want to see if you guys can do it. So I'm going to give you guys some time to find the inverse of g of x when g of x is 3x minus 8 all divided by 5. Alright, it looks like most people are there. Has anyone already decided that that stuff's too much for them? Okay. I told you I was honest. I like to just see it all there. Alright, so then we've got a times by 5. So I've got 5x equals 3y minus 8. Add that 8. So 5x plus 8 equals 3y. And then divide by 3. So 5x plus 8 divided by 3 equals y. I'm going to write it still with the proper notation, but are there any questions about any of that? So g of x then, or the inverse of g of x equals 5x plus 8 divided by 3. We are going to move on to show that type problems. Are there any questions or concerns about variable interchange? Okay, so this first show that problem is actually going to go back to our f of x function. The one we already used, you can see it's up here again. Same f of x equals 2x plus 7. It says show that f of the inverse of f of x just equals x. So, kind of makes, hopefully the thought of this makes sense to you in that if an inverse function undoes whatever a function does, we should end up with just x. It should kind of take away everything and just leave us with x. Keep in mind this is a show that problem, So we want to see all of those steps. I think sometimes people look at this and are like, they do it all in their head and they're like, oh, I get it, but we got to see those steps here. And the first thing you want to do is find the inverse, but we already found the inverse, right? So the inverse we did in that first example, the inverse was, and I'm just going to my notes to make sure I write it down right, x minus 7 divided by 2. Now, whatever you have to do in your notes so that you realize that we didn't just conjure this out of thin air, if you need to draw an arrow up to the first example, whatever, we already did the work for that. So now, if we're taking a look, we've got f of the inverse of f. Remember when we worked with composites, we would write it like this so that we could see what has to go into what. So then as I start this, I'm going to start my f of x function, but I'm going to leave myself a nice big old space for x because I'll have to plug my inverse function into that. So that means this inverse function goes in there, so that is x minus 7 divided by 2. So I put my inverse function into the original function. Like I said, we didn't just make up the inverse function. We already did the work for it. We're just kind of taking it off that first example. Any questions up to here? Because here's the point where I think that some people might look at this and be like, oh, duh, it's just x. But since it is a show that problem, we need to go through that process of showing everything that's going to cancel out and leave us with x at the end. So for example, what happens with these 2's? Those cancel out. So I end up with x minus 7. I don't really need those parentheses anymore because that multiplication is over. So x minus 7 plus 7. What happens with our minus 7 and our plus 7? Those cancel out. And I end up with just x. Like the colors don't work out, but that's okay. So, again, some of you guys might be like, oh, it's whatever, but make sure you show those steps because this is a show that problem. I want you guys to try one of these on your own. Does anyone have any guesses at what the next one's going to be? Yep. You guys got it. So going back to your g of x function, same g of x as it was in the second example, show that the composition between g of the inverse of g of x just equals x. So I'm going to give you guys a little bit of time. Add this. And then we'll go over it real quick. to get that first step. So then we've got these 3's that are canceling out, so that kind of gets rid of those parentheses because that multiplication is no longer there. So 5x plus 8 minus 8 divided by 5. Just like the last one, the plus 8 and the minus 8 are canceling out. So you've got 5x over 5. And sure enough, those 5's cancel out, so it's just x. Anyone have any hesitations with the show that problem or anything with this variable interchange? Because we're going to do the step box and then talk about graphing. So the step box, I kind of couldn't decide, so I put 2 different things in the step box. The first one was, in your own words, describe variable interchange. So whatever you need to make sure you remember that, put that there. And then just kind of reflecting on graphing, because for a lot of this graphing stuff, I do expect you to use your prior knowledge to graph. I'm not going to review a whole bunch of graphing stuff right now, so if you need a refresher, you have a question, make sure you ask it. But there is a technique that I think people sometimes forget about. So when in doubt, what is one method you can always use to graph? Because I know a lot of people would think with like slope-intercept form, y equals mx plus b. You know, we did do some graphing quadratic stuff. But if you come across something funky, does anyone have any thoughts of like what you could do to graph it? Then this is my tip for you. Make a table or an XY chart. Because even if you come up with something that just like looks really weird, you can pick some numbers like -1, 0, 1, maybe even more depending, and you could come up with the y values. You could substitute that in there and come up with a graph for it. So I just like to put that out there just in case, because I know you're not going to have only linear functions, or some of the linear functions you have are not going to be so nice, not going to have as many integers in it. So just kind of keep that in mind. Now, when we talk about the inverse and graphing, graphically the inverse is the reflection of the original function in the y equals x line. So the first thing we have to talk about is, what does the y equals x line look like? Where is the y equals x line? Does anyone think they might know or have some idea of what that looks like or where that line is? No, that was sort of what I was looking for, because that's the same thing that happened second hour. There weren't like words, people were making arm motions that let me know. So go with that. Are you going more like this? Okay. So kind of, and then I had curious like this. What about you? Like this? All right. So if we think about it, and I've got at least one person that's got the right motion, arm motions there. There's a slope of 1. And there is no y-intercept, so it's like a y-intercept of 0. So if we use like y equals mx plus b, that means I start at 0, 0, and I go up 1 over 1, up 1 over 1, up 1 over 1. So it's a positive slope, so it does go kind of up from left to right, and it goes on the diagonal right through all of like those corners there. I don't have a ruler, so mine's not as straight as it probably could be, but yeah, I don't know why that happened. But that's our y equals x line. And so, one thing that we know is that we've got this little rule, and you did this in geometry 2 years ago, and you probably don't remember it, and that is a-okay, because here is the rule. The reflection of point AB in the y equals x line is BA. So again, wasn't expecting you to remember that. I'm telling you right now what that rule is. So, can someone give me like an example over here in like quadrant 4 of a point, any point?
1,
So over 1, down 1, 1, negative 1. So then the reflection of that, so I'm going to call this point A. The reflection of that would be -1, 1. I swap them. So I would have to go -1 up 1, and I'm going to call that A prime. It's an old geometry habit. But that's our reflection. And let's just, I don't know, let's pick another one. How about -5, -3? No, I don't want to do that one. -5, -2. Just another example. So if I have a point at -5, -2, let's say that's B. So then if I switch them, -2, -5 will be the reflection. So -2, -5, that's my reflection. So do you guys see, like, switching them, how we get that reflection? Yeah, but I can even draw a couple lines here. I don't have very many colors left over, but let's say this was my original line right here. Then this is my reflected line. So I'm a little bit crooked, but so we've got these reflections. So you are going to have a few different graphing problems. I'm going to give you some graph paper for them. Again, if you need a refresher on some of that graphing stuff, you'll just have to ask. Any other questions about this or about that reflection? This was just kind of an example to show you guys what that looks like and what that line looks like. Okay. So that is it. Here's your assignment, and I'm about to hand you some graph paper. There are 4 graphs you're going to be asked to do. There are 6 graphs on this piece of paper. The back is blank if you want to do the same thing on all of it, or if you want to cut it out and staple it in your notebook. I don't really care. Whatever works for you. I have had people refuse my graph paper because they had their own. If that's what you want to do, that's good too.